We have our next talk of today, Reverse Engineering Sherlock Holmes Style by Deakin-Sharpe. Let's welcome her to the stage.
Good afternoon, everyone. Thanks for having me today here at BSides. I've been coming for a couple of years and I'm super excited to be able to present a talk here today. As you just heard, my name is Deakin-Sharpe. I'm a malware analyst at the Australian Cybersecurity Centre, which is part of the Australian Signals Directorate. In my team, we reverse engineer malware samples that have been gathered during cyber incidents affecting Australian critical infrastructure, industry, and government at the local, state, and federal levels. When we analyse a sample, there are a couple of things that we're trying to find out. First of all, we want to see if we can identify the malware sample, if it's part of a known malware family, or if it's something completely new. Then we want to find out what its functionality is. What is it capable of doing on the compromised network that we were able to grab it from? Third, we want to know how it communicates, and we also want to see if we can extract any intelligence from it, such as the address of the command and control servers and any passwords. And finally, we want to make sure that in future, we're able to detect it. In this talk today, I am going to take you with me on a journey through my analysis of a sample that crossed my desk last year, which we called TCP Listener. This sample used a really interesting obfuscation technique that made it quite difficult to analyze. So today I'm going to talk about what that technique was and how I overcame it step by step in order to fully reverse engineer the functionality of the implant. But we'll start with the easy stuff. First off, TCP Listener was a PE file, so it's a file that runs on Windows. It contained a configuration block, but it was pretty easy to extract because it was just encoded with an XOR algorithm. When you ran it, it would decode that config and then set up some firewall rules to allow for inbound TCP connections. It would wait for a new connection to come in, and once it received a new connection, it would start waiting for commands. It also used 2 layers of AES encryption on its network, comms. Now, throughout this setup phase, I could see it employing some API obfuscation. And so before I go any further, I'm going to take a couple of minutes to talk about API obfuscation so that we're all on the same page for the rest of the talk. So, all Windows malware, indeed all Windows programs, are going to use native Windows APIs or library functions to perform their tasks. If I want to read a file on Windows, I'm not reinventing the wheel. I'm going to call the API's create file to get a handle to that file, read file to read the bytes, and then close handle to tidy everything up. Now, as an analyst, if I get a binary and I run strings over it, and I see a whole stack of Windows API names, this can give me a bit of an idea of the kind of functionality that might be contained within this implant. And if I go a step further and I throw this binary into a disassembler of my choice, for me that's IDA, and I look at a function and I can see the APIs, create file, read file, close handle, I know pretty quickly what that function might be doing. And malware developers don't want this, right? Like, they don't want my job to be easy. They want my analysis of their binaries to be as hard as possible and to take as long as possible. I think probably they'd be pretty happy if it was just impossible altogether. So one of the techniques they turn to is API obfuscation. What they're going to do, they're going to dynamically load the APIs at runtime. They're going to call load library with the name of the DLL that the API comes from, and then they're going to call get proc address with the name of the API to get the address of that API, which they can then invoke directly. Now, if they leave those API names in plain text, it is going to remove them from the import address table of the PE file, which I guess might have an impact on like AV detection or heuristics and things like that. But it is still going to appear in strings, and if I disassemble the binary, they're either going to appear pretty close to where they're used or in a way that's easy to cross-reference. So that's not going to slow me down much. So they can level up and encode the API names, for example, with an XOR key. This is going to remove them from strings, but it's pretty straightforward to write a decryption script, which you can run statically, and have your IDA database annotated. And of course, if I run the sample, it is going to automatically resolve. This is what I could see TCP Listener doing. They were encoding their API names with an XOR key. Another technique is to hash the API names. In this case, usually on startup, the implant will walk the DLL export table, hashing every API name it comes across until it finds one that matches what it has. This does give a similar level of protection to encoding the API names. It won't appear in strings. It will automatically resolve when you run it. And you can write a script. It's a little bit more of a pain, but it is ultimately pretty straightforward to do. So with all this in mind, let's return to TCP Listener. I had finished with the setup phase and I was ready to start looking at the commands because this is the important part of the problem, right? I want to be able to tell our incident response team what this implant might have done on the compromised network. And just like in the setup phase, most of the APIs were obfuscated with the same technique. They were loaded dynamically and the names were obfuscated by an XOR. But these developers, the malware developers, they'd done something extraordinarily clever, and they had actually removed even the obfuscated names from the binary. Instead, for any given command, the C2 server would send a list of the APIs that it would need to execute that command as part of the command and control payload. So if there was a command for reading a file, the C2 packet would contain the encoded names, create file, read file, close handle, followed by the name of the file that they wanted to read. And this presents something of a problem. Obviously, it's not going to appear in strings. I can't write a static decryption script because the obfuscated information simply isn't there. Even if I run it dynamically, my sample is going to sit there waiting for me to tell it what APIs it's supposed to execute. Now, if we had the controller, we could recover this information, but we don't have that. Our attackers have that. And if we'd had some network packet capture from when the implant was running on the victim network, then we might have been in with a chance, but I didn't have that either. So at this point, I was pretty stumped. I had never come across a problem like this before, and neither had anyone in my team. So at this point, I turned to the words of Sir Arthur Conan Doyle for a little bit of inspiration. Now, this quote was actually spoken by a client of Sherlock Holmes as he came to him begging for help. I don't know what to do, and my whole life seems to have gone to pieces. It's a little bit how I was feeling at that point. I think most reverse engineers have felt like that more than once in their careers. But after my moment of despair, I recovered myself and I decided to listen to the great detective himself. I wanted to see if I could deduce what the APIs were supposed to be based on the information that was still available in the binary. And that's what we're going to talk about for the rest of today. At the time I wrote this presentation, the Microsoft documentation listed 19,795 APIs. But we do have an advantage. So a couple of the DLLs were preloaded as part of the implant setup phase. And where an API came from one of those DLLs, it would directly reference that preloaded handle. So in most cases, we know which DLL the APIs come from. Most of them were from kernel32.dll. That did still leave nearly 1,100 APIs to choose from. There were 2 that came from ADV API 32.dll and 2 that came from an unknown DLL, and its name was passed in to the implant by that same method from the C2 payload. In total, there were 9 commands that used this API obfuscation technique, which left me with a total of 32 strings to deduce, 31 API names and 1 DLL name. Every good detective needs a set of clues to look out for, so these are going to be ours. We're going to use strings and particularly unique constants to help generate ideas. We're going to be matching up function prototypes, so looking at numbers and types of arguments. Context was super important. I typically found if I could get 1 to 2 APIs per command, all of the rest would follow. And furthermore, if I'd figured one command out and I had a shared variable with another command that I hadn't looked at yet, that usually gave me a starting point. I read a lot of documentation and a lot of example code. Malware developers may not always follow best practice, but it is a good place to start. And as a final sort of sanity check, you want to think about, does it actually make sense for the implant to perform the kind of functionality that I'm hypothesizing? Now, just as a warning, when I was in the middle of my analysis attempting to explain to my colleagues what I'd figured out and where I was up to, I definitely looked like that. Hopefully, by putting this presentation together, I've laid it out in a slightly more coherent manner, but you have been warned. We are entering red string territory. And with that, we're going to jump in. So we're going to go through each command in the order that I went through it in, which is roughly going to go from easiest to hardest, starting with Command E. Now, at the top of this snippet from IDA is a bit of a snippet of assembly that is going to appear every single time we invoke one of these APIs, because this is doing our resolution. It's going to take the handle to the DLL that it comes from, along with the string that contains the encoded API name that we got from the C2 packet. It's going to pass that into our resolve API function, where it will do the decode and then the get proc address, and it's going to return the address of our API. But looking at where that actually gets used, we have our first clue, this constant f001f. That's going to be passed as the first parameter into our first function, along with two other parameters, one of which is a pointer to like a string or a byte buffer that also gets passed in by the C2 payload. So that's going to be an input to our command. Moving further down, we see another clue, this global backslash string being built up on the stack. And it turns out if the result of our first function call is null, we're going to call it again, but we're going to append that global backslash string onto the front of our third parameter. We see now our f001f constant pop up again, but this time as a second parameter. We're calling our function 2. We're also passing in the result of our first function call. Then we're going to do a mem copy, and that's going to become our output that we're going to return to the C2 server. And then we've just got two more functions. Function 3 called on the result of function 2, and function 4 called on the result of function 1. And that's our first command. Before we dive into the clues, I want to just take a second to talk about 0. So 0 can represent like the literal value 0 when you see it in the disassembly, but it could also represent a constant or enum with the value 0. It could be a boolean. It could be a size with the value of 0, and it could also be a null or optional value. This is really important to keep in mind once we start trying to match up our function prototypes. Now, starting with our first clue, I think our best clue is this f001f number. It's like a specific looking number. To me, it's most likely a symbolic constant. So in IDA, you can right click and hit use standard symbolic constant. That's going to bring up a list of all of the symbols in the Microsoft documentation that have this value. In this case, there were 3. Looking at each of them, I eliminated the first 2 pretty quickly because they were related to like kernel stuff or driver stuff, and I thought that was probably not likely, which left me with one possibility, file map all access. I took that constant, I threw it into my favorite reverse engineering tool, Google, and I ended up on the documentation page for map viewer file. On this page, I could see this desired access parameter, which has as one of its allowed values, this file map all access constant. At the top, I can also see map viewer file x being suggested as a possible alternative function. So let's look at both of those. Map viewer file x has too many parameters to be anything that we're looking at, so we can cross that off the list. Map viewer file has 5 parameters, and we can see its second parameter is this desired access f001f constant, which means that we're looking at map viewer file as matching up with function 2. I can also see that the first parameter is a handle to a file mapping object, and this is the result of our first function call. So if we look back at the documentation, under the information about this handle, I can see the create file mapping and open file mapping functions return this handle. So now we look at these for function 1. Create file mapping A, too many parameters, cross it off the list, that's pretty easy. Open file mapping has 3 parameters, which matches up. We have our desired access, this f001f again as our first parameter. We have a 0 where we have a boolean, and then we have a pointer to a string for the name. If I go onto this documentation page and look underneath the information about that third parameter, I can see the name can have a global backslash prefix, which matches up with what we see in our code. So at this point, I'm feeling pretty good about these 2 answers. I'm going to update my code and update my list of clues. We're dealing with memory mapped files. Our first function is open file mapping A, and our second function is map viewer file. And now we can see, as we start to look at our third and fourth functions, we have a little bit more information, because I can see that function 3 is taking a file pointer, the result of our second function, map viewer file, and function 4 is taking a file handle, the result of our first function, open file mapping A. So now we return to the documentation. I'm going to be a bit like a broken record for a little while. So for open file mapping A, under remarks, I can see the caller should release the handle returned by open file mapping with a call to close handle. So potentially this is one of our functions. There's also a link to some example code. In my example code, I can see at the top our open file mapping and map viewer file functions. And then the final two functions down the bottom are unmap viewer file, which takes the result of our second function call, and close handle, which takes the result of our first function call. Everything's matching up, so I'm going to call it. Our first command is mapping and reading from a memory file. Now, command 5 had 11 different APIs in it. I'm not going to go through all of them, but I am going to go through the first couple to make sure we get the hang of this process. To start with, the clue that I can see when I look at this is we have a function address being pushed as an argument. This to me screams like threads. You know, we probably want to like take this function and execute it like off on its own. So looking at all of the functions related to creating threads, we have create thread, which looks pretty good. We have like the start address as our third parameter. We have zeros where we have optional values or sizes or D words. We also have a struct where that appears. So, you know, that's looking pretty good. We'll keep that in mind, but we're going to check all our other possibilities first. Create remote thread, too many parameters, cross it off the list. And same with create remote thread X. So we have a create thread call. As a disclaimer, I did also look at processes as a potential here, but I didn't want this to get tedious. So we'll move on. If we go and look then at the function address that we're executing in the new thread, I can see another interesting string being built up on the stack. I'm not going to attempt to read it out. We pass that as the first parameter into our first function, along with 3 other parameters, including as our third parameter, a byte buffer that's empty. So it was created just above this particular code snippet. So we have an empty byte buffer. So I took this string, I threw it into Google along with the name of the DLL that it came from. I did misspell the DLL name in this screenshot, but I didn't get any results. So then I went back and I tried just Googling the string by itself. And I actually got phenomenally lucky because it turns out this exact string is used as an example in the Microsoft documentation. Clicking on this article, I learned that what I was looking at was a string security descriptor. And a little bit more clicking around the documentation led me to convert string security descriptor to security descriptor A. We have our string security descriptor as our first parameter. And our third parameter, which was that empty byte buffer, is actually an output parameter. So this is where we're going to return our string security descriptor to. Typically what I found is that if they were creating a new byte buffer and passing it empty into one of these functions, it was usually an output parameter. So I'm going to update my list of clues. We've created a security descriptor. Presumably at some point we're going to want to use it. Moving on, I now see a new string, this pipe \fd0_ being built up on the stack. Then it's going to append a 32-byte value onto the end of that pipe string. This 32-byte string comes also from the C2 server, so it's another input to this command. Then it's going to take that full string and it's going to pass that as the first parameter into function 2, along with a stack of other parameters. And it's going to get a result and do something with that later. Then we build up another string, pipe \fd1_, and we do the same thing. We append a 32-byte value to it, the same 32-byte value, and then we call function 2 again with a couple of differences in our values of our parameters, and then we get another result. Function 3, we pass it our fd0 result and a 0, but this is interesting because it can throw an error. So it checks the return value to see if it was successful, and then if it wasn't, it calls getLastError and compares the value to hex 217, which means hex 217 is an error code, another clue. We also then go and do the same thing with our fd1 result. So we've got a nice little list of clues. I guess Some of them are a bit suggestive, pipe in a string. But we're going to start with the strongest clue, which is that error code, because we can do the same thing in IDA. We can right-click, use standard symbolic constant, and there's one error code, which is error pipe connected. We go back to Google, we throw that in, and I end up at connect named pipe, which tells me if the client connects before the function is called, the function returns 0, and getLastError returns error pipe connected. So we have connect named pipe as our function 3. I can see that the first parameter is a handle to a named pipe, and we know that that's the result of our second function call. The documentation tells me that this handle is returned by a createNamedPipe function, which is now what we're going to look at for function 2. Our number of parameters are matching up. At the start, we have a string name. The documentation tells me the string must have the following form, this pipe name format. Our second parameter is the open mode. So that tells me that the first pipe is being created with write permissions, and the second pipe is being created with read permissions. All of our other parameters, they check all the boxes. And then we get to the last parameter, which is the security attribute struct, which has as its second member a pointer to a security descriptor, aka the result of our first function call. So we're dealing with creating and then connecting to named pipes. This ticks off all of our clues. So I'm ready to proceed under the assumption we're dealing with named pipes. We've done 4 functions. I will spare you the next 7. Basically, at this point, I went and read all of the documentation I could about pipe functions and all of the example code that was out there about multi-threaded pipe servers. And I caught a little bit of luck. The last 4 functions in this command are in like a sub-function, and that gets reused by command 6 and command 7. Command 5 is going to initialize a pair of named pipes and then read on a loop from the pipe that has read permissions. Whenever it reads something new, it's going to output that to the C2 server. Command 6 is going to close all of the pipes that the implant has open, and command 7 is going to close any given pair of pipes. You'll notice that I've left command 5 in orange. That's because there was one function that I couldn't quite figure out. Like I had an idea or two, but nothing quite fit with what I was seeing in the binary. But I did feel pretty confident in the rest of them, so I decided just to move on and come back to that at the end if I had time. From here on out, I'm going to move a little bit faster. We're not going to go through all the documentation. Yay, I hear you say. But this is mainly because I think you've probably got the hang of it right now. And from here on out, things get a little bit harder because we're not going to have any more strings and we're not going to have any more unique constants. So for command 3, we're going to lean on shared variables to give us a starting point. The first thing that command 3 does is retrieve a shared struct that is written to by, among other commands, command 5, which we just looked at. It specifically accesses the member of the struct where we stored the write pipe. It's going to take that handle and it's going to pass that into function 1 along with a couple of input buffers that were passed in by the C2 server. And then it's going to call function 2 just with that handle. It doesn't really take a genius to figure out what you might want to do with a pipe that has write permissions. I had read, as I said, all of the documentation on multi-threaded pipe servers, so it was very quick for me to hit upon write file for our first function and flush file buffers for our second. Command 3 is writing to our pipe. Command C and Command 8 I have grouped together because they were pretty similar, and in this case the name of the game was pattern recognition. Either I've seen this pattern before in this sample, or I've seen it before in other malware samples. Right off the bat, we have a function address being pushed as an argument. We just saw this in command 5. This is a create thread call. Then, going inside this function, at the very top, I can see this hex 40, hex 1000 being pushed as parameters to the next function. Individually, there are a lot of possibilities for hex 40, hex 1000 in the Microsoft documentation. But they're a pair that I've seen together a lot. These are likely memory protection constants, which means we're dealing with a virtual alloc or a virtual protect call, so allocating or changing the permissions on memory. When you throw in a mem copy and then a call to that allocated memory, this is shellcode. I have seen it many times in malware samples. I think most malware reverse engineers, if you put this in front of them, they could probably identify the missing calls. It turns out that Command 8 is going to execute shellcode that communicates with the C2 server via those named pipes that we set up in earlier commands. And Command C is going to execute shellcode that presumably communicates by some other means, but it wasn't visible to me. We have 2 more commands to go, and from here on out, again, things get a little bit harder because we don't have any context to rely on from here. For Command F, this is all we have. We're iterating through an input list of D words, or 4 bytes at a time. We're passing that into our first function along with 2 other parameters. We take that result, we pass it to function 2 along with a 0. And that's it. I stared at this for a while and went, okay, I guess this has to be my strategy. So I literally sat there and was like, what are some of the things that malware can do? Here's a non-exhaustive list of things that malware does. If we look again at the structure of the code and see if that can lead us in the right direction, broadly speaking, we are looping over an input, getting a result, calling a function on that result, but we're not getting any output. We're not returning anything to the controller. So that probably suggests we're not enumerating anything, we're not reading any files, we're not scraping anything. We are taking some input from the C2 server, but it's an input of D words. So that's not probably enough to be writing to a file. I sort of stared at this for a while and went, I don't know, it does malware does stuff with processes. It's not opening them, it's not listing them. Maybe it's closing them? And that's actually exactly what it was doing. Our input list of D words is actually an input list of 4-byte process IDs, or PIDs. We take each PID, we pass it into open process to get the process handle, which we then pass to terminate process, along with a 0 exit code to make it look like nothing went wrong. We're killing processes by PID. This one is definitely the biggest leap of logic. It does feel like a bit of a shot in the dark, but the evidence backs me up. When I looked online, I could see example code that listed this as a way to terminate processes. All of the function prototypes match up. And more importantly, it worked. I ran it, it didn't crash, and it killed processes for me. So I'm going to call that a win and move on. For our last command, command hex 11, this is where we finally get into that mystery DLL that I mentioned right at the start. So the first thing it does is take the name of our mystery DLL, which comes from our C2 server. It passes that into a function that's going to decode that name and then call load library to get the handle to the DLL. Our first function comes from our mystery DLL, and it has 5 parameters in total. Our second function comes from adv API32.dll. It has 7 parameters, and we're calling it in a loop. So we're going to call it repeatedly. And our third function also comes from our mystery DLL, and it has 1 parameter. So our clues, again, feel a little bit thin. We don't have any strings, unique constants, or any sort of external context. But looking at it, I was well, function 2 has 7 parameters. There can't be that many APIs that have 7 parameters. One cannot search the Microsoft documentation by number of parameters. One cannot even sort the Microsoft documentation by number of parameters. Just as I had resigned myself to a very tedious manual elimination process, my supervisor came to my rescue. He found a GitHub page for an IDA plugin that lets you view Microsoft documentation in IDA. But inside it, it had a list of the MSDN docs as markdown files with 1 file per API. So we downloaded all of those markdown files. Then I would say we abused Yara to search through them. If you're not familiar with Yara, it's the tool that we use to search for malware and identify it on disk using patterns of strings and bytes. I don't think they ever really intended it as a search tool for Microsoft documentation, but it was A, quick to put together, quick to run, and most importantly, it worked. So this is a truncated example of one of those markdown files. Of particular interest to us are this required DLL line, which tells us the DLL that the API comes from, and these parameter strings. So for function 2, we wrote a rule that searched for the DLL being adv-api32.dll, and we wanted that parameter string appearing exactly 7 times. And we actually got a manageable number of results. So I went through each of these and narrowed it down to 4 possibilities. They were all to do with looking up accounts, either by name or by SID, with ASCII or wide strings. At this point, I didn't have enough information to further narrow it down though, so I decided to see if the same approach could work for function 1. Now function 1, we don't know what DLL it comes from, but we do know 3 DLLs that it doesn't come from. So we can eliminate those and then look for exactly 5 parameters. Unfortunately, that was still nearly 1,500 results, and I was not going to go through each of those by hand. So, returning to where the function gets invoked to see if that can give us any more clues. Turns out the 4th parameter is one of those empty byte buffers that was created just above this code, which means it's probably an output parameter. And then when you look at where that actually gets used, it turns out when we're iterating over, through that lookup account API and calling it repeatedly, we're actually iterating through our 4th parameter, which suggests that it's probably a list. We then take each item in the list and we access an offset of hex 10 inside each one, which suggests it's probably a list of structs. And then we take that struct member and we pass that as our 2nd parameter into our lookup account API, which means it's probably it is an account name or the account SID. Now, all of this information is a little too specific to triage down from 1,500 files, but I guess broadly speaking, function 1 is getting a list of something. Luckily for me, Microsoft has some fairly standardized naming conventions. So I took my list of API results and I grepped for APIs containing the keywords list, net, group, or enumerate, because I figured these were likely to return a list or a set of something. And this got me down to a reasonable number of results to look at. I went through each of these one by one until I hit upon the answers. Our mystery DLL is WTS-API32.dll. Our first function is WTS enumerate processes A. As its 4th parameter, it has an output parameter, which is a list of process info structs. And our process info structs have, at offset hex 10 inside them, a pointer to the user SID. This means that our 2nd function is lookup account SID, either ASCII or wide, it doesn't really matter. And our 3rd function is WTS free memory. We're enumerating processes, and then for each process, we're looking up some additional information about the account that started it. Now, I could have called it quits here. I do have an overall picture of what the implant's doing, but I really hate not having greens across the board. So I decided to circle back, and I wanted to see if my new approach with the Yara rule could help me figure out what my missing function was. So our final function is function 4 of command 5. It takes the handle to our write pipe, a pointer to a D word, which contained the value 5, and 2 zeros. Writing my Yara rule, it comes from kernel32.dll. It has 4 parameters, and I know that one of those parameters is a handle, so I'm just going to look for the word handle appearing anywhere in the file. That gets me down to 89 results, which is manageable, but I think we can do better. Function 4 doesn't return any output. It doesn't appear that we do anything with the return value, and it doesn't have any of those empty byte buffers being passed in as a parameter. So it's unlikely to be getting something, and it's unlikely to be creating something. So if we eliminate API names with those words in them, I get down to 39 results. Again, the exhaustive approach. I went through each of these one by one, eliminating all the possibilities until I had one answer left. But I wasn't entirely happy with it. On the surface, it looks pretty good. Set named pipe handle state seems like a thing you might want to do to a handle to a pipe. We have a handle to our pipe as our first parameter, a pointer to a D word, the pipe mode, so that's the mode that we're going to be setting on our pipe, and then 2 optional values. And I had actually already considered set name pipe handle state. It appeared in a bunch of the example code that I had. The problem is this value of 5, because 5 is not a valid pipe mode for this API call. We return to the final time, to the documentation. So the mode for set name pipe handle state is a combination of 2 flags, a wait mode flag and a read mode flag. If you're not familiar with how flags work, here's a little table. Basically, each flag is represented by 1 bit of a number. In this case, our wait flag is our least significant bit, 0 for wait and 1 for no wait. And then our second bit along is the read mode, 0 for byte or 1 for message. You take that number and just read it as decimal. That gives you the allowed values of 0 through 3. We have the number 5. If we extend this table out a little bit and add 5 in, we can see that we'd have the no wait flag set. We have a read mode of byte, but then we have another bit set. We have a third bit set, but we only have 2 flags. So looking now at the context in which this is called to try and tease out what's going on here, we start by creating the named pipe to get our handle. We then call connect named pipe, which is going to wait for a client to connect to the other end of that pipe. And then we would be calling set named pipe handle state. Looking at the function prototype for create named pipe, I can see that the third parameter is the pipe mode, which does make sense, right? If we're going to be able to change the pipe mode, we probably want to create it with an initial mode to start with. In this case, we're starting with a value of 4 and changing to a value of 5. When I look at create named pipe, I can see it does have a third flag, this pipe type flag. So it gets a much bigger table. We now have 8 different possibilities. We have, wait and no wait, read mode byte, read mode message, and type byte and type message. We're creating our pipe initially with a mode of 4, so we're starting with wait, read mode byte, and type message, and then changing to 5, where we have our no wait, read mode byte, and type message. So to try and pull all the pieces together, 5 is not a valid pipe mode for set named pipe handle state, but it is for create named pipe. The call would be changing our pipe mode from 4 to 5, and because the wait flag is set by the same bit, we'd be flipping that flag from wait to no wait. And because we're calling this after calling connect name pipe, this does make sense to me. We're calling connect name pipe and we want to wait until someone connects to the other end of the pipe before we return. But after that, maybe when I write to this pipe, I don't want to wait for the stuff to be written into the pipe. I just want to throw it in and then come back and it can sort of process in its own time if it's going to block for a while. More to the point, there is no other API in the Microsoft documentation that makes sense. I know. I checked. My final conclusion then was this. I think the developers made a mistake. And that's maybe a little bit nice to see. I'm looking at a pretty sophisticated implant with this novel obfuscation technique that caused me no amount of headache over that week. Maybe it's nice to see that they are human after all. And I can kind of see how it happens, right? You set your variable for the pipe mode, you set out your combination of flags, and then when you go to, change the mode, you just sort of set, you just flip the bit and then reuse that variable rather than checking and seeing what flags are actually used by that particular API. It does run without crashing. And I can see this as being the sort of thing that like you may not notice immediately operationally. So now we have greens across the board. Our complete picture of what the implant is doing looks like this. We are mapping and reading from a memory file. We are able to create a set of named pipes and then execute shellcode that communicates with the C2 server via those named pipes. We can also execute shellcode that communicates by some other means. We can then enumerate processes and kill processes by PID. And just like that, the day was saved, Australia was defended, and our nation lived to fight another day. The reality of it is this. I packaged up these findings and I passed them on to our incident response team, who were able to use this to further inform their investigation into this compromise. This was one small piece of the puzzle in that incident, but it was a really interesting one. It was certainly my favorite sample that I looked at last year. And, it forced me to get creative because we'd never come across anything like this before. And I think any day that you get to be creative at work is a really good day. So I hope this was as interesting to you as it was to me and that you've learned something today. I'm going to leave you with a quote from Sherlock Holmes from The Hounds of Baskerville. You know my methods, apply them. Thank you very much.
A great talk from Katie. Do we have any questions in the audience? To put your hands up. There's one up the front here.
Look, first up, great talk, and I read about you were a software developer and you became a malware reverse engineer, if that's correct. So similar stuff with me. I'm a software developer. I'm currently studying the science reverse engineering course. So there are some very well-known, my question is around some well-known malware. So there's some very well-known malware. I'm not going to take the name due to obvious reasons. So the way they infect you is the very people that are supposed to protect you. For example, one of the biggest recommendations from the Cyber Center itself is do regular updates. And there are very well-known malware out there that actually infect people through those very mechanisms that are supposed to protect them. Mm-hmm. Like, for example, if you've looked into mobileware, you'd just go and download a ride-sharing app thinking you're downloading a ride-sharing app, and what you would get is a ride-sharing app laced with some shell code, and you run it, and they're going to get a shell on your device. So have you come across mobile malware like that? And if you have, how do you protect that, given that the very own people that are supposed to protect you are actually infecting the devices of ordinary citizens? So what's your recommendation? How do you decode it? I'm still learning malware reverse engineering, so I'm new, but you're quite well versed. So how do you detect those type of attacks?
So how do you detect them, or how do you
how do you detect and protect against them? Because if the very mechanisms that are supposed to protect you become the attackers, what do you do?
So I guess I'm not someone who does, hardening of systems or, defending against them. I look at the samples that are put in front of me and reverse engineer them. And I haven't done a lot of looking at mobile type malware. So yeah, I'm afraid I don't have a great answer for you. Sorry.
Any other questions for Oh, there's one over here.
Thank you for your wonderful talk. I'm still new in cyber, and I'm a little bit surprised that you use the same tools like us and go through the same very complicated process. I'm wondering if we could build a box that, like a virtual machine, that intercept every call to the CPU and to the system, so just to make all the activity transparent and a lot easier to a special system for DFIR.
Yeah. Sorry, can you repeat the question? I couldn't quite hear it.
Can we use a dedicated system built for DFIR, a mock system that actually intercept all the calls to the system, so to make the program activities very transparent?
So as in, would having, program hooking, would that have helped in this case? Is that, API hooking? Is that sort of what you mean?
Exactly.
Yeah, so I guess if that had been on, the victim network when this implant was running live, then yes, something like that would have helped. But the thing with this implant was like, even when you ran it, like if I ran it in a sandbox, it would literally sit there like waiting for my fake C2 server to tell it what APIs to execute, because it would send a list of the ones it would need for every command. So no for me as the analyst, but yes if something like that had already been on the compromise box while the implant was like talking to the attackers.
Any other questions? Oh, right in the center. Give the mic runners some exercise today.
Thanks for the talk. It was a good talk. So just wanted to know, what other information could have helped you, speed up the guessing work? If you had, more information, what would that be in this case?
So in this case, I think the most helpful thing would have been if there had been network packet captures from when this implant was running, because we had the keys to decode those AES encryption layers, and then we probably would have seen those tasking payloads coming in with those lists of API names. So I think in this case, that's probably the only thing that would have helped. Yeah.
Thank you.
There's one straight behind you, if you want to catch that one.
Yeah, fantastic presentation. From what you saw, was there any form of attribution? Were you able to attribute this to any particular group or any particular nation state? I don't know if you can particularly tell us. And from what you found in this, have you identified any commonalities with news samples you've seen recently?
So my team, any good team, has a bit of a meme stash that we've built up over the last couple of years, and we do have one that relates to attribution, which is the Chadwick Boseman Black Panther. We don't do that here. So my team doesn't deal with attribution. What I will say in this case is looking at the technical indicators. This was part of a sophisticated compromise. It was a bespoke implant, and it was using really novel obfuscation techniques. So from a technical point of view, for me, it definitely feels more APT-ish than crimeware-ish, but that's as far as I know for the attribution. In terms of further samples, I haven't seen anything else that uses this particular technique, and I haven't seen any further samples since we looked at this incident.
So very bespoke.
I think so.
We have a question up the front here. Getting lots of questions. That's good.
You said this gave you a big headache over a week.
Yeah.
So did you do this whole thing over a week?
Yeah.
Wow.
So the initial analysis.
Definitely a round of applause for that.
Thank you. So the initial analysis, I'm excluding outside of that week. I think I started looking at these I realized that the API information wasn't there on a Friday, and I think I had figured all of the APIs out by the following Thursday afternoon or Friday morning. It was a fun task. I had a really great time.
One more question up the back. Oh, sorry. Right here. Sorry, miss.
A real quick question. Because just taking this idea a bit further of I don't know, obfuscating what you're doing, do you see much, I guess, the next step in my mind, if I was a malware writer, would be a writing my own interpreter or something like that, and then executing my malware in brainfuck or something. Is that something you see?
So I guess the closest thing that we see that can give you a bit of a headache is stuff that's virtualized. So things that use VM protect and stuff like that. That's I think anyone who reverses malware will tell you that's a bit of a pain. Yeah.
Just behind.
Thank you for the talk. You mentioned there were 2 layers of AES encryption and you had the keys. Can you say anything about how you got them, or does someone else figure that out?
No, they were inside the binary.
Oh, they were hard-coded in. Okay, thanks.
There's a gentleman in a red shirt who's had his hand up for a while at the
back.
by the back.
Great. It was really good to hear. And so how did it land on the machine? Do you have any context as to what it was trying to do?
So I don't have any like further context today about like how it got there, but you know, this sort of functionality, and given the sort of APT-ish lens versus the crimeware-ish lens, like they tend to gather information more than they tend to be like trying to ransomware your computer.
Any other questions? Oh, we have one over here. You're just going to be here for the rest of the day? That's right, we do have a bit of time.
I'll be down the front. I left some time.
Yeah, it's good. It's great.
Thank you. I ran down to ask this question. So you mentioned when you analyzed the shellcode execution part that so I guess my question is more, did you see in the struct that it passed if there was references to either the SMB pipe handle for it to communicate via shellcode back to the C2, or was it kind of like from your assessment it would just execute the shellcode then kind of die and not communicate back to that C2 head end?
So I guess the information that I had regarding the execution, because I did say like one of the commands, I'm like, yeah, it communicates by the pipes, and the other is like some other method. The reason that I said it was like by the pipes is because like before it executed that shellcode, I could see it checking whether those pipes had been initialized. So my assumption was that it communicates by those named pipes. But beyond that, I had no information about how it was getting back to the C2 server.
So I guess as a quick follow-up, sorry, thank you for your time.
That's all right.
Were you able to see how the struct was constructed before it got past that function for the shellcode invocation to call the in memory?
I could, and I'm trying to think back because it is a little while ago, but I don't think the structure of the shellcode gave me any further information. Like I think they just did like the data that was passed, like there might have been a size for like how much shellcode was to follow, and then it just copied that much memory in and then executed it. I think some of them were also like under some XOR encoding as well, so it would decode.
So I guess it didn't pass anything via like the parameter to the new thread or whatever.
Yeah.
Cool. Thank you. Appreciate
right.
that.
Oh, there's one there.
You know, regarding the stuff where you were figuring out, you know, the DLLs or the functions with certain number of parameters. Mm-hmm. In that situation, you used Yara, but did you try using like ChatGPT or, you know, any generative AI for this kind of stuff? Would that help?
So at the time, I didn't think of it. It's not really something that I tend to reach for as a tool. But like in anticipation of this question at conferences, my colleagues and I did try putting it into one of the GPTs, I don't remember which, and we said, okay, give me all of the APIs in ADV API 32.dll that have 7 parameters. And it basically said, do it yourself. It didn't phrase it exactly like that. It said, oh no, that's a bit too complicated for me to do because there could be all of these different versions of ADV API 32.dll, but here's how you would go about doing it. You could parse the export table and then go through each API one by one and see if they have 7 parameters.
I'm going to try this.
So my approach was better. I'm not saying that a more skilled prompt engineer couldn't like get it out of a GPT, but I guess as well, like, you know, I think Sherlock Holmes would probably agree that to make accurate conclusions, you have to be able to trust your data. And the fact is, I wouldn't trust one of these AIs not to hallucinate API calls. So, you know, if they hallucinated an API that was totally made up, then that's one thing that's like pretty easy for me to check. It's annoying, but I could do that. But I wouldn't trust it not to miss things. And so I would not know if I was working with incomplete data or not. So, yeah.
We could probably take one more question, or are we done? Excellent. Another huge round of applause for Katie.
Thank you.
Brilliant.